Welcome back. Today we are going to be starting Chapter 1 with Section 1, looking at rates of change and limits. There is a lot of stuff in this section, but a lot of it's not particularly difficult. It might be kind of weird at the beginning, but the math behind it's not too bad. So our learning targets for the day, we're going to find average and instantaneous velocities. We're going to use properties of limits to find limits. We're going to determine when limits can be found using substitution and then find the limit if possible. We're going to find limits using tables or graphs, and we'll find one-sided limits. So average and instantaneous velocities. We saw this a bit in that chapter P activity. An average velocity is just the distance that has been traveled divided by the time that has been elapsed. So we have just the final distance minus the starting distance divided by the change in time, or change in distance divided by change in time. Another way that this could be written, as opposed to delta t, a lot of times we write it as an h instead. It just helps to keep the equations just a little bit less daunting. Like one Greek letter out of it helps a bit. And so, if we wanted to find an average velocity, we'd want something to find it of. So let's say a rock falls from a height. This distance can be measured by y equals 16t squared. It's projectile motion just dropping down. Where y is the distance traveled and t is the time in seconds since it started to fall. So if we wanted to find the average velocity for the first, say, 2 seconds, what we would do is we have the final distance, that would be f of 2 minus f of 0, because that's where we'd start. Start at 0, go to 2, over change in time was 2. So we'd plug in 2, we'd have 16 times 2 squared, minus plug in 0, 16 times 0 squared, divided by 2. 16 times 2 squared is 4, times 16 is 64, minus 0 over 2, and then 64 divided by 2 is 32 feet per second, is the average velocity as the rock is falling for the first 2 seconds. Now the rock starts out not moving at all, and then it speeds up. So it's going to start out slower and end up faster, but the average velocity is 32 feet per second. Same thing as I'm driving into work every day. I don't always go the same speed, but my average velocity is going to be the total distance divided by the total time. It's 11 miles divided by half an hour makes me go 22 miles per hour on average. Yes, sometimes I'm going faster, sometimes I'm stopped, but that's what the average velocity is. Now an instantaneous velocity, that's going to be the velocity that it's going at a specific time. Now the problem with that, as we saw in chapter P, is that at a specific time, there is no change in distance and there is no change in time. So we end up with 0 divided by 0. So we can't find an instantaneous velocity as itself. However, we can find upper and lower bounds for it. We can find what the fastest and the slowest it could be is. And so to do that, we would find we're using the same thing, and we're just looking at 2 seconds. So this would be from 2 seconds to just over 2 seconds. So sometime over 2 seconds, could be at 3 seconds, could be at 2.1 seconds. We don't know. We can change what that h is. And this one's from just under 2 seconds to 2 seconds. So we can look at the an average velocity right above and an average velocity right below the time in question. And that should give us bounds for the instantaneous velocity. Like, what would it be at that point? Now, we can't just plug 0 in for h here, because if we do, we get 0 over 0 still. So that's problematic. We can simplify, however. If we simplify these, I'm going to take this one over here. We have delta y over delta t is going to equal 16 times, we can distribute that, 4 plus 4h plus h squared minus 16 times 4 over h, delta y over delta t equals, we can distribute to get 64 plus 64h plus 64h squared. Nope, 16h squared. How could you guys let me do that? That's 16h squared, because there's not a 4 in front of that one, minus 64 over h. And then what happens here is we have a 64 minus 64. Those guys disappear. Now everything has an h in it. We can factor an h out. 64 plus 16h over h. The h's cancel, so our delta y over delta t for the time interval just over 2 seconds is going to be 64 plus 16h. Now if we do the exact same thing with the other one, we can follow along with the same steps, and we're going to get delta y over delta t equals 64 minus 16h. It's going to switch places there. So what we have is we're going to have one that's just a little bit bigger and one that's just a little bit smaller. Now if we take values of h and we plug them into a table, we're going to get a table, but we're going to get a table that's going to go right down here in this left-hand corner. So I'm going to erase just a little bit of this, because it's definitely going to cover up what we're going to look at. If you didn't get it, it's gone. You'll never see it again. There's no possible way you could rewind this until before I started erasing and see what I had just erased. So that's a pity. All right, so now we have our table here. And so if we're plugging in 1, it's from 48 to 80. It's a pretty big gap. But as we're plugging in smaller and smaller numbers, we get numbers that are really close to 64. And so we'd imagine that that's going to be 64, because, and that should make sense, as h is getting smaller and smaller, this 16h is getting smaller and smaller, and so it's just getting closer and closer to 64. So if h is 0, we'd think, hey, that's going to be 64, but h can't be 0 because it's still undefined in that original equation. So, but we can get really, really, really close to 0, and the upper and lower bounds are getting it closer and closer and closer to 0. And what that is that's called a limit. The definition of a limit is, there is an official definition, which is really kind of long and complicated. I didn't even bother putting it in here. It's in your book. It's actually not even in the section. It's in an appendix if you really want it. It is, you can look it up. It will not help you understand it much. But what a limit is basically it is what we would expect the function to be if it's what we would expect the function to be based on the points around it. So like on that one, it's getting really close to 64 from both sides. We'd expect it to be 64. If we plugged it into a calculator, we would get an error at that point. But if we covered that up and we just looked at everything around it, we would expect it to be 64. That's what a limit is. So the notation here, we have this lim, that's short for limit. When I write it, it is in cursive. I write two different things in cursive, limit and logarithm, which is great until we have the limit of the natural log. Gets a little bit confusing, but that's just kind of how it goes. But this is read, the limit as x approaches c equals L. Oh, of f of x. I've forgotten of f of x in there. The limit of f of x as x approaches c equals L. That's how we would say that that particular sentence. So we have a lot of properties of limits. First of all, we have a couple limits that we can assume. The limit as x approaches c of k equals k. So if k is a constant, it's a horizontal line. As x approaches a number, it's still going to be that horizontal line. It's still going to be approaching that one value that it is for everything. And the second one, the limit as x approaches c of x equals c. The whole y equals x thing. Well, as x is getting closer to c, y is also getting closer to c. So that's what that one is. And now for our properties, we're going to define a couple limits. These aren't specific, it's just notation so that we can talk about these properties. So we're going to have a limit as x approaches c of f of x equals L. So L is the limit, it's a number, f of x is a function, doesn't matter what they are. And limit as x approaches c of g of x equals m. So we have some properties. We have sum rule. The sum rule says if you're adding them, then you just add the limits. So what that means based on the limits that we have, the limit as x approaches c of, we'll go x approaches 2 of x plus 3 equals, we can split this up. What's the limit as x approaches 2 of x? Well, that uses this one. So that's going to be 2 plus, what's the limit as x approaches 2 of 3? That uses this top one because 3 is a constant, so that's 3. 2 plus 3 equals 5. So the limit is x approaches 2 of x plus 3 equals 5. That's the sum rule. The difference rule, I bet you can't guess what this is going to be. It's the same thing except with subtraction. We're not going to do an example on that one. The product rule, same thing actually except with multiplication. And so here we have two different functions multiplied together. It's going to give us L times M. So if we had, say, the limit as x approaches 2 of, let's let f of x be x plus 3 because we know what that limit is. It's 5. And then m, we'll just have that be x. So as we're doing it, we just multiply. We know that the limit as x approaches 2 of x plus 3 is 5 from that first example. And the limit as x approaches 2 of x is 2 because of that. We know what the limit as x approaches x is. So 5 times 2 is 10. So the limit is x approaches 2 of x plus 3 times x equals 10. And that just uses the product rule. Most of the time when you're using these, you're not really going to be thinking about them. You're just going to do them. It's kind of like the properties of equality when you are solving an equation. The constant multiple rule. That's if we have a constant times a function. The limit is just the constant times the function, or the limit, which the k, we could use this top one and use the product rule. So this is kind of redundant. But if we had, say, the limit as x approaches 7 of 3x, that's going to be 3, that k, times 7 because of that second limit that we know. So 3 times 7 is 21. So the limit as x approaches 7 of 3x is 21. We could get this by going, 3x is just x plus x plus x, so we could use the sum rule to do that one as well. Quotient rule. Same basic idea. If you're dividing functions, you can divide the limits. As long as that denominator doesn't equal 0. That makes it problematic. So if we had, say, the limit as x approaches, I used 2 and I used 7. We'll go 2 of x plus 3 over 3x. Well, we know the limit as x goes to 2 of x plus 3 is 5. We've seen that a couple times. Over the limit as x goes to 2 of 3x. Look at the previous one. If we had limit as x goes to 2 instead of 7, you see we'd have just 3 times 2, which would be 6. So it's 5 over 6. And the power rule. The power rule says that if you have a power and a limit, that's the same as the limit of the power. So if we had limit as x goes to 2 of x to the 4th, that's going to be, we know what it's going to be the limit as x goes to 2 of x to the 4th. We know what the limit as x goes to 2 of x is. That's 2. Then we just have to take that to the 4th, which is 16. So those properties of limits, again, there's a bunch of them, but chances are if you had to guess at what a lot of these would do, you would probably guess correctly. More properties, these are specifically for polynomial and rational functions. Polynomial functions, if f of x is polynomial, then the limit as x goes to c of f of x is just f of c. We can plug in that value. And the reason for this, we could do a proof for as big of a polynomial as we want. That is fairly complicated, but let's look at the limit as x goes to 2 of, let's say, 3x squared plus 7x plus 4. We can split this up so that we can use properties for this. So we can split up the addition, we can split up the constants. We can go, this is going to be the same as 3 times the limit as x goes to 2 of x squared plus 7 times the limit as x goes to 2 of x plus 4, the limit as x goes to 4 is 4. And so we split this, and basically the x's just got replaced with the limit as x goes to 2 of x. Well, what is the limit as x goes to 2 of x? It is 2 squared plus 7 times 2 plus 4. So essentially, what we just did is we took that number and we just plugged it in for each of the x's. That's the same thing as substituting. That's just f of 2. So that's what this is saying. If you have a polynomial function where there's nothing funny going on, everywhere you look on it, it's going to be exactly what you'd expect it to be based on what's around it. So you can just plug in the values. All the things we did on the last page were polynomials. Rational functions, basically the same. If f of x and g of x are both polynomials, then the product, or the quotient of f of x over g of x will equal f of c over g of c, as long as g of c does not equal 0. There's that whole can't have 0 in the denominator thing again. And that we could show the exact same, we just do it for the top and the bottom. But we'll say, we'll do an example instead. Let's limit as x goes to 3 of 4x squared minus 7 over x cubed plus x. So we have 4x squared minus 7 over x cubed plus x, limit as x goes to 3 of that. We're just going to plug in 3. 4 times 3 squared minus 7 over 3 cubed plus 3. 3 squared is 9 times 4 is 36 minus 7 over 27 plus 3. 36 minus 7 is 29 over 27 plus 3 is 30. So the limit as x goes to 3 of 4x squared minus 7 over x cubed plus x equals 29 over 30. And notice I didn't use the properties. It was, I mean, you could see the properties in there if you really wanted to, but we just plugged it in because it's a rational function, so we can use substitution. One-sided and two-sided limits. See, I told you there's a bunch of stuff in here. One-sided and two-sided limits. One-sided limits, there's two of them. There's coming from the right-handed limits. That's where, so we're going to have limit as x goes to c from the positive side. That's from the right of f of x. That's not an exponent, it's more of an index. And we have left-hand limits, which is where x goes to c from the negative, from the left of f of x. So what are those? Well, if we're looking at something like this graph here, the right-handed, the limit as x goes to negative 5 from the right of f of x. So negative 5 is here. Coming from the right, we're coming from this side. Where is it going? It's going to 3. And then the limit as x goes to negative 5 from the left of f of x, that would be coming from this side. It's going to 1. So those are those two limits. At 0, right here, the right-hand one is going to be 1, and the left-hand one is negative 2. At 3, both the right and the left are going to 1. It doesn't matter that this guy's up here. The function does not have to be defined for the limit to exist, because it doesn't matter what that value is. It's about what's around that value. We're covering up that value. So that one, both of them would be 3. Two-sided limits. A two-sided limit is the limit. That's like the normal limit. And it exists if and only if both of the one-side limits exist and are equal to each other. So for negative 5 and 0, the limit does not exist because we could not cover up that value and just kind of know what it's going to be, because it's going to two different things. So the limit does not exist there. However, for 3, the limit as x goes to 3 from the right side of f of x equals 1. The limit as x goes to 3 from the left side of f of x also equals 1. So the limit as x goes to 3 of f of x exists and equals 1. So that's the idea between one-sided and two-sided limits. Every once in a while talking about this, we use what's called the floor function or the greatest integer function. And what that looks like is that. And what that does is it cuts off the decimals. It does not round, it rounds down. So something like 2.78, the floor of that is just going to be 2. And it graphs using it's a stair-step graph. So that's what the floor function is. If you see it, it is mentioned in the book. You can see it there too. On the squeeze theorem. What the squeeze theorem says is that if you have a function f of x that's between these other two functions for all x not equal c, it doesn't matter what happens at c, but for all x near c, and then the limits of the two outside ones equal something, then the inside one also has to equal something. The limit has to equal that same thing. It squeezes it to the middle. If it's always in between them and the limits go to the same thing, that means it has to be there too. So an example of this, a lot of times this uses sine and cosine because they oscillate and they have a minimum and maximum value, which also helps. So we want to show the limit as x goes to 0 of f of x squared times sine of 1 over x equals 0. We can't just plug in 0 because sine of 1 over 0 becomes problematic. We could graph this. If we graph it, it looks kind of like that. So as x is getting closer and closer to 0, it sure looks like it's getting closer to 0 as well. But how are we going to show that? Well, we need a function above and below. What we know about sine of anything, we're going to call sine of 1 over x, is always in between -1 and 1. So we know that this function, this x squared times sine of 1 over x, will always be x squared sine of 1 over x. It'll always be bigger than -x squared and less than positive x squared, because we can plug in -1 and +1 for sine and get this going to be there. If we graphed this one, we would get our graph, and then we have the positive and negative x squared. So we can see that it's pinching it right into the middle. Well, what is the limit as x goes to 0 of -x squared? And what is the limit as x goes to 0 of positive x squared? Well, those are both polynomials. Plug in 0, plug in 0. So if we take the limit of all of these, we're going to go up here. We're going to take the limit as x goes to 0 of -x squared. Has to be less than or equal to the limit as x goes to 0 of x squared times sine of 1 over x, which has to be less than or equal to the limit as x goes to 0 of positive x squared. We know those two end ones are 0, so we have 0 is less than or equal to the limit as x goes to 0 of x squared sine of 1 over x. It's less than or equal to 0. Well, what is both greater than or equal to 0 and less than or equal to 0? It has to be 0. Therefore, by the squeeze theorem, limit as x goes to 0 of x squared sine of 1 over x has to equal 0. So The squeeze theorem comes in handy from time to time. Honestly, don't use it that much, but again, it does come in handy now and then, so it's important to know. And this was it for section 1. We will deal with a different kind of limit in section 2, but a lot of stuff happened in this section. So I'll catch you at section 2. I'll catch you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.